All right, so as for today, we're going to look at the Chapter 5 Part 2 lecture, all right, which again is not on the quiz. So we have everything, all material for the quiz, which is 1 week from today. Gonna get started on this material. All right, so that way, because I'm always worried you guys will be like bored and won't have enough to do. So basically, I want to make sure that we're ahead of the game there. And then also as a note, so if you want to turn in your activities progressively, highly recommend that. I can give you feedback and stuff like that. And be aware that like, so each activity is worth 10 points. So if you turn in one activity and you get a 10 out of 10, it looks like you have a 10 out of 20 or 10 out of 30. All right, so just be aware of that. All right, any questions or concerns before we get rolling? All right. Okay. So now we're actually getting into the unit circle, which we've already talked a little bit about. And this adjusts to using the Pythagorean theorem, all right, a squared plus b squared equals c squared, with our point AB, aka x comma y. But now, all right, r squared will always equal 1. And just to be clear, what a unit, all right, a unit circle, unit vector, anything to that measure, it means it has length 1. So our R value will always be up to 1. What this means is the unit circle is based on, now all those values become fractions, all right, and decimals and small numbers. So in order to make, all right, the hypotenuse of every single triangle equal to 1. All right, and that's what's on our cheat sheet. So taking our same SOHCAHTOA that we had, if I replace R with R equals 1 in everything, notice that everything gets simplified. All right, sine, which was y all over the hypotenuse, all right, now becomes y all over 1. Similarly, cosine. Cosine is now x over 1. And this is what I was talking about when we were talking about the quadrants. X, all right, directly then relates to cosine. Y directly relates to sine. Because, all right, when dealing with the unit circle, then that exact number, the point on the edge of the unit circle for pi over 3, all right, we can find exactly what that coordinate is for sine and cosine, and then all other corresponding trigonometric functions. This then restricts, or maybe gives us, a particular domain and range for our trigonometric functions. And so sine and cosine will always range between -1 and 1. And the concept there is that with our unit circle, the edge points, since it has radius 1, it'll always be down to, positive. It'll always be 1 at the furthest points. And so x, right, ranges between -1 and 1, which is cosine. Y ranges between -1 and 1. And the proof of that is simply that sine of theta equals b all over r, where r is 1. So sine of theta actually equals b, and b is in the actually technically range of -1 to 1. Hence, sine of theta is then in the range of -1 to 1. All right, this is a proof, but I mean, proof is barely the right word. This is more just the logical justification, all right, that it goes between -1 and 1. And the whole thing we're going to talk about today is our actually graphing of the functions. So on the unit circle, representing sine as y and cosine as x, we can identify points. But what we're actually going to be interested in is, what are the graphs of these looked at graphed on the XY coordinate system? So in order to do that, we need to talk about some things we've already talked about. Coterminal functions, which actually translates to period. Periods, or periodic functions, like all trigonometric functions, they have a particular look, right? Amplitude, period, phase shift, x, y shift, all that stuff. But then, all right, once you identify a single period of it, it repeats over and over and over again, every 2 pi, right, for the basic functions, and then every corresponding period for any adjusted function. And so this comes back to coterminal angles. When finding these values, all right, when I find the exact value of a function, all right, all I have to do is cut off the number of periods that I'm looking at. What this also adds is that actually tangent and cotangent are repeated every pi instead of every 2 pi, like sine and cosine and their reciprocals. So it's even easier because since sine divided by cosine is tangent, right? All the values on top are exactly the same as all the values on the bottom, and the sines are the same as well. Which means if I have tangent 5 pi over 4, that is actually tangent of pi plus pi over 4. Which is just tangent of pi over 4. I didn't even need to use reference angles there. Period equals pi or tangent theta. And then tangent of pi over 4, which we can identify on our unit circle. All right, but this is the best one. Pi over 4 is by far the best one because sine of pi over 4 equals cosine of pi over 4, which means tangent is something over the exact same thing, and you don't even have to know what it is. What's anything over itself? 1. Ah, doesn't get much better than that. Similarly for cosine, right? And if you can't immediately look at this and pull out how many 2 pi's is 11 pi over 4, break it down as a fraction. 2 pi equals, actually, let's do this. 2 pi over 1, turning that into fourths, becomes 8 pi over 4. And then I can pull it out. 8 pi over 4 plus 3 pi over 4, which is cosine of 2 pi plus 3 pi over 4. And since, again, periodic, this becomes cosine of 3 pi over 4. And where is 3 pi over 4? In what quadrant? AKA 3/4.
The third quadrant.
Third quadrant is down here. Is that 3/4 rotation around the Cartesian plane?
Would be the second quadrant.
Second quadrant. All right. So, all right, remember that a full rotation is actually 2. All right, 2 pi. All right. So, yes, this is 3/4 of a revolution. All right. But remember that I'm actually talking about 3/4 of pi. All right. So, yes, I did say that a little awkwardly because I'm always just cutting off the pi to see how far I'm going. So, we're actually right here which is 3 pi over 4 is the angle. And now we're going to use reference angles. If that's 3 pi over 4, what is the reference angle? What is it? Yeah, 1/4 pi over 4. This then becomes cosine of pi over 4. And then, now remember with reference angles, once you translate from whatever the full angle is to its reference angle, we have to identify the sign. Cosine corresponds to x. Is x positive or negative in quadrant 2? Negative. X is negative, right? That's an algebra fact. And then we look up cosine of pi over 4, which is our 1 over root 2. All right, so just making a reference. And it's reference. So, all right, notice that we just keep using, and when I'm saying period is basically what we were calling coterminal. All right, the difference between coterminal and period is only for tangent, because tangent has a period of pi, right? Instead of having to cut off 2 pi, you could just cut off 1 pi. But coterminal for sine and cosine is exactly synonymous with period, all right? So whether you call it, and you don't have to, I'm making a note of this is a period, this reference angle, just so we know all these facts that in just 2 weeks, we've accumulated a ton of information, right? I was like, trig is so interesting because it's all the same stuff, it just keeps building. All right, along those lines of continuing to build information, even in odd functions. So again, we're going to look at the graphs of these functions and we're going to get there in just a minute. But one other big thing, all right, to help us identify angles is remembering the properties of even and odd functions. So, and this is again, algebra, right? An even function, right, is symmetric about the y-axis. Can you name a very, very common, right, the epitome of an even function? Not a trig function, just from algebra. What is the most famous even function? One that is symmetric about the y-axis. Anyone know? Y equals x squared. What does y equals x squared look like? What's the shape? I know you guys know this.
Parabola.
It's a parabola, all right? AKA a U, right? That is the epitome of an even function, one that is symmetric about the y-axis, all right? An odd function is a function that is symmetric about the origin. That means it's quadrant 1 and 3, and similarly 2 and 4, are negative inverts of each other. Does a function come to mind that is an odd function? This one's slightly harder. What is that the graph of? Anyone know?
It's like cubic root.
That's a not cube root. That's just a cubic. All right. Cube root is actually an odd function as well. You're absolutely correct, because a cube root looks like that, right? Same thing. All right. Both of those are examples of odd functions. Yes. So an odd function is kind of harder to like recognize. All right. An even function where it's super easy to recognize. But if you recall in algebra, the proof of this is when you put in a negative value, right, it comes out the same as the positive. And we can do that for the parabola, right? When I put in positive 2, 2 squared is 4, negative 2 squared is 4, right? Cubic, I can do the same thing. 2 cubed is 8, negative 2 cubed is negative 8, right? So And that's how you identify even and odd functions, like through process of values. What that actually, remembering our even and odd functions, what that actually gives us is that when we graph these functions, all right, these functions, trigonometric functions, are both even and odd. Specifically, cosine and its reciprocal, secant, are even functions, all right? Sine, tangent, and their reciprocals are odd functions. And what that actually in trig, that has an additional property, all right? That when you have a negative of the angle, you can actually pull it to the front. So sine of the negative angle is same as negative sine. I mean, that is the definition of even and odd, but it was never really helpful to us with polynomials and algebraic functions we looked at. With trigonometric functions, since we're always finding angles, being able to pull that negative sign out to the front is very, very helpful. Now, be aware, this is just another shortcut, all right, of graphing the angle and using a referencing. Because if I graph negative 45 degrees, right, I know the reference angle of that is 45 degrees, and then I would just determine the sign of the trigonometric function. So this is just another technique to help us identify angles. And the point is, there's lots of ways to do it. Even and odd is just really, really nice because the negatives are always something that just annoy us. So if I have negative 45 degrees, because sine is odd, that becomes negative sine of 45 degrees. And sine of 45 degrees is 1 over root 2. Now again, I could have graphed this angle. Negative 45 degrees is this. The reference angle of negative 45 degrees is actually 45 degrees. And then I would say, oh, sine in quadrant 4 is negative because sine corresponds to y. Oh, so it ends up being negative 45 degrees anyway. So whether you use even and odd properties or reference angles, it is the same thing. Whichever one is easiest for you. All right, similarly, cotangent. Negative 3 pi over 2. All right, so again, using our properties of even and odd, cotangent is an odd function, which becomes negative cotangent of 3 pi over 2. And then similarly, all right, cotangent's not one I know at all, so I'm going to do the reciprocal, which is tangent. And now, all right, this is where the unit circle starts to really come into play. 3 pi over 2, that's actually not our, like, one of our 3 big angles that we said. Pi over 3, pi over 6, pi over 4. All right, but 3 pi over 2 is actually a pretty easy one on the unit circle. Where is 3 pi over 2?
It's not the second quadrant.
Second quadrant? 270 degrees. Ah, see, so we keep going back to degrees. Where 270 degrees is exactly where?
Right there.
There. All right. So again, we're going to keep practicing. That's 0. All right, radians. 0. That's pi over 2. That's pi. That's 3 pi over 2. And then this becomes also 2 pi. All right. So, all right, I know radians is the big one, and this is why we can keep in the beginning. It's very common, convert to degrees, all right? But I'm going to keep talking in radians because trig is all about radians. And ideally, I'm trying to think. I was like, basically after this first quiz, we got to be borderline done with degrees as far as your familiarity between radians and degrees. You want to be able to recognize all our angles in radians. Okay, we'll come back to degrees again, but all right. Okay, so that means our angle, so we're down here, which is 3 pi over 2. And cotangent, which actually now I think about it, I didn't actually have to flip. So actually, I'm going to go back to cotangent. and cotangent, which is 1 over tangent. Tangent is sine over cosine. But actually, the other way to do that is, that's why I want to go back, since 1 over sine over cosine is just cosine over sine. So it actually didn't help me to do the reciprocal function here. And here's where the unit circle comes into play so much. All right, so if I have my unit circle, this point down here, that is a point x comma y. And we identified all the points on the outside. These 3 points, all right, this point right here is the point 1 comma 0. This point right here is the point 0 comma 1. This point out here, negative 1 comma 0. And hence, this point down here is 0 comma negative 1. So this is actually really, really nice. Since I have cosine over sine, right? The cosine point here is, for a cosine of 3 pi over 2, what is it? What is it? Thought I heard it.
0 comma negative 1.
Sorry?
We were looking for the point.
Yeah. What is cosine of 3 pi over 2? What is its value? Cosine corresponds to x, which means,
-1.
is that the x value?
0.
0. All right. This is, right, x comma y, right? These are x comma y, which means that's what I was talking about. The edge values are the best ones, right? If I was just looking for cosine of 0 is what?
1.
1. Sine of 0 is what?
0.
0. And so every point on the edge of the unit circle, specifically on the axis, right? On these 4 points, all right, you can get those values very, very fast. So back to our problem. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. So I have negative 0 divided by negative 1, which is, need my calculator, 0. I was like, so this is the real help of the unit circle, all right? With these particular values, I can find sine and cosine, and hence every single reciprocal function very, very quickly. This does bring up one other thing. So right here, it says domain of tangent and secant functions, odd integer multiples of pi over 2, 90 degrees, cosecant and cotangent, all right, integer multiples of pi times 180. Okay. That's because what we just looked at here, with the 0 and 1, so pretend this said cosine of pi, or sorry, cotangent of pi. If this was cotangent of pi, that means it is the cosine value divided by the sine value. What is 1 divided by 0? What is 1 divided by 0? What do we call that value? Remember? Undefined, right? Remember now? So that's the point. Whenever I have 1 divided by 0, and that occurs dependent upon what I'm looking at, all right, tangent or cotangent, for which one is the denominator, right? Whenever I end up with one of these zeros in the denominator for cotangent, and for cosecant as well, right? Sine of 0 is 0, but cosecant of 0 is 1 divided by 0, all right? Which means I have an undefined there. So in those points, all right, we end up, and usually when you divide by 0, what does that look like on a graph? All right, the most famous one, of course, being y equals 1 divided by x. The graph looks like this. What do we call right here? What do we call that? Oh boy, we're really testing our algebra knowledge, huh? Asymptotes. All right. So we have these asymptotes. So we end up with these asymptotes all over our graphs. All right. Do you see why Trig is so awesome? Look at all the algebra you have to keep remembering. All right. Because the more math you learn, the more math you keep pulling from. All right. The stronger your algebra is, and I tell you this, in calculus, I swear to God, all I'm teaching people is algebra. Because if people have stronger algebra skills, calculus is a breeze. Trig is a breeze. All right, so keep practicing that algebra. If you see an algebra skill that you're weaker in, practice that up. Go back. All right, the book we have, right, the book we're using is the algebra book. Okay, so it's algebra and trig. So scroll through this section or that section, you know, and we're going to keep doing lots of algebra with our trig. Okay. All right, so now this comes to the graphs of sine and cosine. What do these actually look at? All right, so I'm going to draw it, and then you're going to put it in your calculator so you can see it, how it looks there as well. All right, so I'm just going to draw one period, but these graphs go on forever, and they are periodic, meaning this one period repeats over and over and over forever. Okay? But we want to identify one period and make sure that we see the important points on that one period. So we already discussed some of it. The graph ranges between negative and positive 1 on the y-axis. Additionally, when we were looking at the unit circle, we saw some important points. Sine of 0 is 0. Additionally, sine of pi is 0, and 2 pi, and every multiple of pi. So every multiple of pi. So at 3 pi, this goes back up and comes back down. So, and that's why when you look at this on your calculator, it just goes forever and ever and ever. We have some other notes. Pi over 2, it reaches its maximum, and 3 pi over 2, it reaches its minimum. So let's go back to our algebra again. How many points do you need to graph a line?
2.
2. How many points do you need to graph a parabola?
3.
3. I see how this works. All right. In order to graph a cubic, how many points would you need?
4.
4. And it keeps going like that. And FYI, these are the minimum number of points, and they have to be the correct points in order to graph these functions. Okay, can't just pick any 3 points. Okay, so like when you're graphing a parabola, one of those points has to, like, the vertex is pretty helpful to be one of those points. So in order to properly graph, all right, any trig and, well, okay, sine and cosine and their reciprocals, I need 1, 2, 3, 4, 5 points to graph one period of a trigonometric function. All right, I need its maximum, its minimum. All right, and then basically sine is the clearest one because notice we have the start, all right, the middle, and the end. And because at this point, the graph just repeats. All right, let's look at this on the calculator, and I want to show you a couple things. So on your calculator, go in, all right, put sine of x in there, and hit graph, and depending upon what your scale is, mine's almost. And if you have your standard graph, That thing looks like an absolute nightmare. Okay,
Or it looks like. Cause you gotta change it with that.
right. So go into Zoom and number 7. What does number 7 on Zoom say? A trig. Look at that. Zoom trig. Now graph it again. Does that look a lot better? Now, notice what else you see there. It's going forever. We graphed, all right, so on Zoom trig, notice those points. It gave, all right, they're not labeled, okay? But that first hash, that's pi over 2. That second hash is pi, third hash, 3 pi over 2, 2 pi, etc. Now, be aware, for standard trigonometric functions, Zoom trig is great. But unfortunately, when we have y equals x squared, is that the only way that graph occurs? No, right? Y equals x squared can become and it gets all messed up. We're going to do all these same things to the sine graph because that's what we do. You have a base function, but the base function has its uses. But in order to apply it to other things, that base function gets adjusted. So be aware. The Zoom trig function, very, very nice for standard graphs. And I show it to you because when we start messing with the trig functions, like we do with our algebraic functions, all right, you want to keep remembering, what does the base sine function look like? What's the standard sine function look like? All right, so you can go in and you can plot it and keep remembering, oh, that one was pi over 2 and that and that and that, okay? And so, but all we ever graph, because typically what we're concerned with is a single period, all right? And typically we graph the quote first period because we want to identify the 5 important points, all right, on basically any trigonometric function. All right, so again, along those lines, right, domain is all real numbers, range is -1 to 1, all right, sine is odd, has a period of 2 pi, its x-intercepts are multiples of pi, the y-intercept is 0, 0, its maximum is 1 at multiples of pi over 2, and its minimum are multiples at basically 3 pi over 2 multiples. Similarly, for cosine. Cosine and sine. Remember that sine and cosine are co-functions of each other. What was that angle, or what was that theorem called? What was the abbreviation we used for it? Functions and their co-functions when they're off by 90 degrees, or pi over 2. Had a nice little acronym of a house pet. CAT, right? The complementary angle theorem. All right. So the truth is that sine and cosine look almost identical. They're only off by pi over 2. The first period is the difference. The first period is the same thing, but it's shifted. So we still have, all right, it is still a repeating function. It still ranges between +1 and -1. The values are just slightly different. It crosses the x-axis for cosine of pi over 2. It has its minimum at pi, crosses the x-axis at 3 pi over 2, and then reaches a maximum again. So cosine starts peak to peak, right? Basically, one period of cosine is peak to peak. Sine does a full, beautiful rotation. Sine is much better to graph because it's much nicer when you have a full rotation. This is technically a full period of cosine. It just doesn't look as pretty as sine. And so go back in your graph, don't delete the sine function, put cosine in there as well. And graph it. And when you line them up, this is where you guys have, this is why I love having a color, right? Yeah, can you see, so you see the red and blue lines? Exact same thing. Do you have color? No, do you have color? Oh, okay. This is the one part where color is nicer. Most of the time it doesn't matter, I have that forever. I was like, so, all right, same graphs, just shifted by pi over 2. Just slightly shifted off. All right, so one vote period, but again, these graphs go forever. So along those lines, all the properties of sine and cosine are almost identical. Domain is all reals, range -1 to 1. Cosine is even versus sine is positive because of that shift. All right, period to pi, same. X-intercepts, Y-intercept, I mean, all these are the same properties, just shifted over. And this is what I was talking about. The relationship between sine and cosine is a small shift on the x-axis. And that's what we're going to look at. So, knowing the base graphs is important. We use the base functions of sine and cosine a lot. But when we start applying these to contextual problems, all right, we need to be able to shift, and we need to know how all of that reacts. So when adjusting our base functions, right, in algebra, we had several properties, you know, x shift, y shift, what we called, you know, we called it kind of amplitude then, I can't remember the word. Basically, how narrow or fat the graph is, and then a sign out front if the graph is flipped, right? So the reflections, we do all that same stuff here, all right? But we have a couple more properties because we need more points, all right? There's trigonometric functions are more complicated than our, like, whatever they are, 6 base algebraic functions. So a couple of notes. Amplitude. Amplitude is the easiest one to understand. That is the top value, all right, to the middle of the graph. So basically, from the minimum to the maximum is 2 times the amplitude. So if you find the lowest point, all right, and the highest point, divide that by 2, and that's what we call the amplitude of a sinusoidal graph. And when we say sinusoidal, this includes sine and cosine, right? Because they're co-functions. All right, period. So the equation for period. And so basically these functions. All right, so this one comes back a lot. Period, which we represent with t, is 2 pi divided by omega. Omega is a piece, all right, that is in the generalized equation of a sinusoidal function. Now the good news for our basic sine graph, omega is 1, right? Because 2 pi divided by 1 is 2 pi, and we know that's the period of the base sine function. Some things that are the same. A negative on the graph flips it about the x-axis, all right? So this is and just like with when graphing algebraic functions, this is the last thing you do. You graph the entire equation, and then you do the negative that is out front, and you flip it. Oh, phi, all right, so we're learning lots of Greek letters. Phi divided by omega, which we'll find in our basic function, is the phase shift. We also call this the x shift. All right, so we need to find this value from the pieces within our graph, right? And that is our x shift. And remember, this works just like it did with algebra. It is the opposite sign. If it is a positive value, that means I'm actually shifting left. If it is a negative value, you're actually shifting right. And then b, right, is our shift on the y-axis, right? And we call that one the y shift. So that's moving the graph up or down. The basic way that sinusoidal graphs are written, y equals a sine omega x minus phi plus b. These pieces are easy to identify. B, that's our X shift or Y shift. That one's super easy. The tricky part is how this inside is written. Because we just said our X shift is phi divided by omega. So while you can find that, what you really need to do is factor inside the sinusoidal graph, factor omega, so you end up with X divided by, so you end up with X minus phi all over omega. So most of the time, we will see it written like this, or we will adjust it to be written like this. So we have our pieces individualized. I have my amplitude, I have my omega, which relates to the period. I have my X shift, I have my Y shift. And it's just much easier to pull the pieces out when we have them in this form. And notice that the standard form is X minus the X shift, because this implies it's always going to the right. It's always a positive shift. If this value is positive, that means the shift is actually to the left. All right, so it's always opposite direction. Opposite direction of sign. And be aware, all right, this is just like, I mean, the sine part is new and amplitude is technically new, and we have omega and phi, which we used to just call, I don't know, K's and H's and stuff. This is an algebraic principle, all right? This actually isn't trig, all right? This is graphing functions with algebra. We're just applying a trig function to it. All this leads to the graphing strategy. Identifying the Y shift, crazy easy. Identify your amplitude, right? And the best way to do this is minimum, best way to do this is amplitude equals, let's see, max minus the min divided by 2. All right, so your maximum value minus your minimum value divided by 2, all right, should give you your amplitude. Period, all right, that depending upon omega, we can then adjust that. And then our X shift, which is also our starting point, all right? Because for our base sine and cosine graphs, they start at what value on X?
0.
0. They start at 0, right? For the first period, right? Technically they go forever in both directions, but we're always going to be about graphing one complete perfect period, all right? So after we identify that, we need 5 points. Our starting point, which is our X shift. Then you find your end point. Well, the end point is the starting point plus the period. And then you find your halfway and your quarters, basically, right, doing what midpoint, right? You know, basically how you do median, right? This value plus this value divided by 2, right? This value plus this value divided by 2. And so we just keep cutting the graph. We cut it basically into quarters, and we'll have ourselves 5 points. Okay. So that's quite the strategy. Let's do this thing in practice. All right, so we have, all right, our basic sine function. And we want to keep practicing graphing this. So our basic sine graph. Pi over 2. This is the first quarter. All right, so we call that guy Q1. This, all right, pi, and I call that Q2. 3 pi over 2, aka Q3. And technically Q2, which is equal to halfway. And so for our graphing strategy, this is basically how we find it. We have our starting point, right? We have our ending point, then we find our halfway, then we find our first quarter, then we find our third quarter, all right? We need to find all 5 of those points, 5 points for one period. All right, we find those 5 points, all right, and then we'll graph it out. Okay, so couple of easy pieces first. A, which is our amplitude. That is 3. All right, so that means we're going up 3 and down 3. That means the entire range of our graph is actually 6. Okay. Omega is 4. Omega is used to find the period. That's really the only functional use of omega. So, the typical sine graph has a period of 2 pi. This has a period of pi over 2. So an entire rotation of this graph is going to happen every pi over 2. And we're going to plot this on our calculator too and see how much worse like the calculator becomes. This is why there is no good way to do this on the calculator. Okay, let's see, what else do we have? B, which is the Y shift, which is 2. And then our X shift / starting point is pi over 3 positive, opposite sign. If it is a negative there, that means I actually start this pi over 3, all right, in the positive direction. Okay, so we identified all our information, all right? At this moment, I only have actually, even though we identified all that, I only have 1 point, my starting point. But this is where that graphing strategy comes into play. And so basically, all right, I know I start at pi over 3, start plus the period gives me my ending point. And, all right, what else this is nice? This gives us a chance to practice getting used to pi's, right? It is just fraction math, but this confuses people often. So we really just want to practice this, right? Pi over 6 plus pi over 2. What's the common denominator? 6. Not a difficult concept at all. But when we have a pi in there, everybody just freaks out. So practice common denominators with pi's. All right, there's my ending point. And then notice that each piece I get, I'm just pulling from what I previously had. So the start point, which was pi over 3, plus my end point, which I just found. And conceptually, that's all it is. Then just a little bit of fraction math with pi's. So that's pi over 6, which makes that 2 pi over 6. And then notice, right, our fractions getting more and more complicated. They're gonna keep getting bigger and bigger denominators. All right, that's 3 points. 2 more. All right, what I call Q1 quarter, which I've labeled as first quarter. Is everyone okay with the calculations that we're doing, right? Again, haven't even graphed it yet. Got a lot of setup, so we have all the info, so we can actually get there. All right, and lastly, our 5th point, Q3, halfway plus the end. What was halfway? End 5 pi over 6. Half was 7 pi over 12. Okay. All right, which gives us 17 pi over 24. Now again, all right, and actually, Macy, you said it before. Sometimes we read this as 17/24 pi. Don't forget that it's just a fraction with pi attached, okay? So if you're having trouble and we're about to set up the graph, like identifying, now I have them labeled right as Q1, Q3, so I know which one it comes first, second, third, fourth, fifth, okay? But sometimes get in our mind about how big is 7 pi over 12? Is 7 pi over 12 bigger than 11 pi over 24? We'll go back to the fraction, right? 7/12, and if you're really struggling, put that in your calculator. It's going to be like 0.6, right? 11/24, that is under half, right? 0.45-ish, okay? So, all right, we have them labeled as we go, but sometimes like the connection of, don't forget, they're just numbers with a pi on them. All right. Okay. Except, actually, I probably shouldn't draw it like that because, all right, this, all right, now we got to start messing with our initial graph. This is shifted on the y up 2. Now, how that works, you start at the middle. The middle of this goes up 2. Okay, so that means our new middle line is at 2 instead of 0. Actually, I need to adjust how I was going to draw this. All right, and 2, so actually I'm going to need it about here. Okay, so we got the 2. All right, additionally, so best place to start is our first point. So our start point is pi over 3, which our typical start point is 0, 0. But now that moves out to pi over 3, all right, and is moving up 2. All right, so I have that is my actual starting value. All right, then our first quarter on our standard graph goes up to its maximum. All right? At the first quarter point, and our maximum was 1. Okay, but now our maximum, since our amplitude is 3 and we started at 2, what is our new maximum?
6,
Almost
4.
5.
5. All right, so our new, actually, let's draw it like this. Our new baseline is that guy. And, all right, we hit our maximum, right? Our first quarter point is 11 pi over 24. All right, so our graph goes up to its maximum. Then, all right, for the halfway point, it comes back down to its baseline. All right, where it crosses the x-axis, and that's why I wanted to draw that on there. So we have our baseline, all right, and our halfway point was 7 pi over 12. So it comes back here, where that is 7 pi over 12. Then, all right, our third quarter point, it goes down to its minimum. All right, the minimum on the standard sine graph is -1, but because of all our shifting, what is our new minimum now? Charlene?
Negative.
Thank you, Charlene. Yes, absolutely. 3 up, 3 down. And that's why I wanted to draw some of the graph here. -1. And my third quarter point is 17 pi over 24. And then lastly, for our end point, it comes back to baseline at 5 pi over 6. So it's the same graph, but all this stuff, right? Look at all that got changed. Okay, so now, as best as we can, graph's totally not to scale. And that is one complete period of this adjusted sine graph. Then, as a note, it did say one last thing, right? It said, then flip it. Now be aware, all right? Technically, I could have drawn the flipped version immediately, but it's just usually too hard because you're comparing this back to the initial sine graph, which you're still getting your mind around. It's better to just graph it. And then I just draw the flipped graph, which is all the same stuff. But basically those two are changed, right? So this guy is y equals -3 sine of 4 x minus pi over 3 plus 2. The blue line, y equals 3 sine 4 x minus pi over 3 plus 2. I wrote that correctly, right? 3, 4, yes. So, same graph, all right? The only difference, negative or a positive. All right, to the calculator. Okay, so I'm gonna keep sine on there. And then this, all right, is the downside. All right, so yeah, looks really nice on coloring. So the red is this one, okay? The blue, all right, and this, you can actually tell that, but just, it's so pretty on coloring. So basically, this is my point, all right? The calculator can help us to some degree, but there's just no way to graph a good function. And here's the other thing, all right? Now your scale, how are you gonna find, let's even say the x-intercept? Are you gonna be able to find it exactly on the calculator? No, because pi is an irrational number. And it is just a total mess, all right, with the calculator. So, all right, we want to be able to graph one complete period, and that's all we're ever looking at. Because again, all right, took 5 points. In order to graph a second period, how many points do I need? Well, technically I already have 1, so 4. I need 4 more. All right, then I need 4 more. All right, I was like, so it becomes, we want to get the main concept of what this graph looks like with an appropriate scale, all right? But we usually typically don't graph more than 1 period, all right? And the calculator can help to some degree, but do not, when it says graph, this equation, I do not want to see like what you put in the calculator, okay? We graph 1 period with good labels, because again, the calculator, it's not going to have good labels either. The important part is, where's the start? Where's the end? Where are the maxes and the mins? All right. We want to identify all that. All right. Because when we look at some examples in context, that's what we're going to need. Okay. All right. Similarly, let's look at our other graphs. Now, again, we're back to base functions here. So tangent, one nice period of tangent. Tangent is kind of a funny one because 1 complete period, all right, this is our first graph, where 1 period is actually in both the positives and the negatives. Tangent should actually look pretty familiar. That's the graph of tangent. What does that look just like? A cubic. Yeah, tangent is actually, looks very, very similar to a cubic. The difference being, important points, looks very similar on a small scale, but what a cubic does not have is an asymptote. As well as tangent is basically cubics periodically. Because tangent repeats, all right, in both directions, all right? So it keeps tangents over and over again. All right, but this value right here, pi over 2, this value here, negative pi over 2. Tangent, all right, unlike sine and cosine, actually increases to positive and negative infinity, but has an asymptote. Now, on the graph, tangent's actually not too bad either on the calculator. So clear up, clear. All right, put tangent in there just so you can see it on our Zoom Trig scale. And tangent, I'm trying to think, is tangent the only one where? Tangent is the only one that actually goes into the negatives when we count what we call the first period of tangent, right? Actually extends into the negatives. But, all right, that's basically the tangent graph. It's actually much, much easier, right? All right. Tangent, you need really only 3 points. You need its origin point, then you need its 2 asymptotes. Because these basically extend forever. So tangent, you actually only need 3 points. That's actually kind of nice. All right, and again, domain, multiples, except for where it has asymptotes, range is all reals. Tangent is an odd function because it looks just like a cubic. All right, it has period of pi, all right, and notice, right, negative pi over 2 plus pi over 2, how far is that?
2.
Is that 2? Pi over 2 this way, and basically pi over 2 this way. How wide is it?
Fine.
What is it? Pi. All right, that is pi wide, and then it repeats, and that's what the period of tangent is, just pi. All right, so tangent's actually easier than that. All right, and then x-intercepts every time, you know, periodically, and the y-intercept, all right, only going to be one y-intercept, and vertical asymptotes all over the place. So the good news, all right, adjusting tangent, way easier. So we got a couple things going on here. We have a negative, all right, so that negative, all right, that means we're going to have to flip it. And then what does it mean when it's, you know, inside the trig function and it's got plus there? What does that mean on the graph? Is that the y shift? That's the x shift. All right, when it's inside the function, that's x shift. When it's attached at the end, that's the y shift. So tangent, all the trig functions, they have the same properties. Now, good news for us, all right, tangent could be adjusted periodically, but be aware, note for tangent, t equals pi over omega. So instead of 2 pi over omega, the period is 2 pi, or is just pi over omega. Now, the good news is if I put an amplitude on tangent, right? If this was 5 tangent, what does that look like? Right? So if this is the graph and I change the amplitude to 5, how does that really look different? The answer is it doesn't. The 5 just means that this slightly increases faster, but it's going to hit this it's going to get near this asymptote eventually, right? So actually amplitude doesn't even affect anything for tangent functions. So the only things we're going to need to look for, right? Some possible period adjustments. All right, I mean, x shifts, y shifts, those can still happen. But like, because tangent is like an easier periodic, it's way simpler. We're not trying to find 5 points. Basically, you find 3 points, and really 2 of them are asymptotes. So graphing tangent, way simple. So we have a flip, right? I have an x shift, all right, of negative pi over 4, aka pi over 4 left. All right, it's always the opposite sign. If this is a positive, that means I'm actually going backwards, pi over 4. The period is still pi, all right, and we're going to flip it at the end. All right, so what's also nice is that I don't have to work super hard to graph this. Except I need a little more on this side. Okay, so instead of starting at 0, 0, all right, there is no y shift. So I'm starting at negative pi over 4. And then I basically just have to figure out, okay, pi over 2 in both directions. So to find the asymptotes, it's basically your start point plus or minus the half the period. In this case, my start point is negative pi over 4 plus or minus half the period, which is pi. So pi over 2. And that's basically how we find the asymptotes. It being that we're just finding a couple of x values, okay? So then I have, all right, negative pi over 4 plus or minus 2 pi over 4 to get common denominators. Okay, so let's see, negative pi over 4 minus 2 pi over 4 is negative 3 pi over 4. And the other value would be positive pi over 4, 2 pi over 4 minus pi over 4, which makes positive pi over 4.
So you can do that slower, but I mean, because it's pi over 4s, it's easy math.
Right? It's halves and quarters. So that means negative 3 pi over 4 here and positive pi over 4 here.
Hence, my blue line is y equals tangent of x plus pi over 4.
But we were actually looking for y equals negative tangent of x plus pi over 4.
Which means that whole thing, flip it across the x-axis. And that gets what we're actually looking for. And again, this is the quote first period of tangent. This keeps going forever, right, in both directions. But all we're ever really going to be looking for is the first period. All right? Okay. Yeah, it's 212. Okay. All right, good stuff. Okay, so that is, again, chapter 5, part 2. We will continue that week after next. All right, next week, all week, we have chapter 5, part 1 stuff. On Tuesday, again, not lecturing. If you have questions, please come. Let me know. Otherwise, I mean, it's more an optional day more than any day is optional. All right, and then 1 week from today, we have our first learning opportunity. All right. You guys have yourselves a wonderful weekend, and I will see you next week.
Sir, speak for.
Sorry.